show and podcast of the Society of Graduate Students here at Western University. I am your host tonight, Gavin.
And I'm your co-host tonight, Elizabeth Mohler.
And we are joined with Vidhya Ganesh Rangarajan from the Earth and Planetary Science Department here at Western University. How are you doing tonight?
I'm doing great. How about you?
We're good.
Yeah, I think we're doing pretty good. Your work as a graduate student, you seem to have a very big focus on one planet in our solar system, and that is our neighboring red planet, Mars. So do you want to maybe quickly tell the audience what it is your research is about?
Okay, yeah. So Mars is actually host to a lot of active surface processes, very similar to Earth. So my research particularly focuses on trying to identify these processes and tracking them using remote sensing images, and trying to basically understand what they entail to how the planet has evolved over time, either in the past or even the present scenario.
And these surface processes, so I'm guessing you're referring to ones like wind, looking at water, maybe something similar to what glaciers do on Earth?
Something like that, pretty much. So active surface processes are not as limited on Mars as compared to Earth. There are a lot of active surface processes on Mars, which probably might include something like dunes, which are common in Earth as well, gullies, and there are some processes that are like strictly seen only on Mars, something like frosting and defrosting processes that we see on the poles, formation of something called as spiders, which I think when they first detected it in 2006 or 2007, when we had high resolution data sets, it was pretty startling because nobody had ever seen something like that before. So my research is particularly focused on what exactly are the agents that are causing these processes, and how do they tell us something about what are the atmospheric components that are responsible for this. And this is kind of like critical because they help us probably help us predict what the atmosphere would be like in the future, especially when you have probably human landing missions or something like that on the surface. So having a better idea of what the current surface climate is on Mars gives us a better chance to predict what the climate might be when humans land in the future.
And why are some of these surface processes unique to Mars specifically?
The current understanding is that the Martian atmosphere is so very different as compared to Earth. Particularly, it's rich in carbon dioxide. Almost about 97% of the atmosphere is carbon dioxide. So very different from Earth is that most of these processes, even like frosting and defrosting, is governed by carbon dioxide frost instead of water ice frost that is commonly seen on Earth. So since the chemicals that are responsible for all these processes are different, they sort of tend to have different surface expressions on Mars as well.
Yeah, and I think you mentioned one of these surface expressions a moment ago. You called it, was it as spiders?
Yeah.
So can you quickly, I guess for the audience, quickly, if you can describe what it is this would look like? Does this look like an actual spider on the surface of Mars?
Okay, yeah. So it's kind of very similar to that. What exactly happens is in the higher latitudes of Mars, during the winter seasons, frost actually gets accumulated on the surface and forms something called as dark spots. These are generally seen along dune fields, the northern polar dunes. And when it actually moves into the spring and summer seasons, these small dark spots, they tend to defrost and cause lineations on the surface. They're not exactly spiders, but I mean, they look very much like spiders, and people still don't know why they actually form in the first place. The current theories are like probably it's just carbon dioxide frost getting deposited on the surface, and it just gets sublimated later on when summer sets in. But it's still a topic of hot debate right now.
So you mentioned something.
Yeah, sure.
You mentioned something really interesting, seasons, and I'd never thought about Mars having seasons. So, what would be the average temperature during, say, a winter or a summer season on Mars?
The highest temperature, at least in the latitudes, in the equatorial latitudes, is probably somewhere around 15 degrees Celsius. That's the maximum it can go, but never really goes that much. The average temperatures roughly vary around minus 50 degrees in the summer, and it goes almost up to minus 150 to 200 degrees in the winters, pretty much. The stark difference in seasons between Earth and Mars is its longevity of the seasons itself. Now, as compared to Earth, the orbit of Earth is almost circular. It's nearly circular, but the orbit of Mars is way elliptical. So the prime difference is that there are some seasons which are extremely long, and there are the rest two seasons which are extremely short. So, like on an average, say the northern spring and summer are almost about 6 months long, but the northern winter and fall seasons are like somewhere around 4 months across. So there's this huge disparity in the length of each seasons that we see on Mars as compared to Earth.
I'm guessing compared to Earth seasons, as you said, with the changes, with the complete difference in how long each season is. So since you've mentioned winter and summer, and I think you mentioned spring, but are they the only seasons that Mars has? Is it not as defined as the seasons that we have here on Earth?
So yeah, the definition of seasons is relative actually in Mars, because I mean, humans have not been on the surface to actually see and identify, okay, this is what is happening during the season. So it's more of a mathematical approach of the season itself. So we define seasons with something called as a solar longitude. So that basically is dependent on the position of Mars on its orbit across the sun. So when it's farthest, generally, when Mars is actually farthest, then we have the northern summer. I mean, the transition between northern spring and summer, roughly around 180 degrees of solar longitude. So how the seasons actually change on Mars is that 0 degrees of solar longitude essentially means that Mars is entering into northern spring or southern fall. And then every season changes at 180 degrees of solar longitude at different portions where Mars is along its orbit across the sun. So it's more of a mathematical approach rather than what changes we see on the surface of Mars, the definition of seasons itself. Yeah.
And I think you touched on this before, but how long would a season, say, winter be on Mars?
So it depends on which hemisphere we are talking about. The northern hemisphere winters are pretty shorter. They are somewhere around 4 months across. But the southern hemisphere fall and winter seasons are almost around six months long. This is essentially because Mars is actually way far from the sun during the southern fall and winter as compared to the northern fall and winter when it's really close by. Because the orbit of Mars is really elliptical as compared to Earth.
Okay, that is quite interesting. When I think a lot of people don't really realize that our planet's not the only one that has seasons.
Yeah,
Maybe not.
I did not know that. Learn something new.
Yeah, maybe not the exact same, since we have some that are lasting for 6 months. But I guess depending on, I know from the United Kingdom, we essentially have one season, which is just rain in fall, rain in the winter, rain in spring, and rain in the summer as well. So, but going back to, and you're talking about surface processes and active ones in particular. So how is it that you get to observe them? Do you get to look at data sets from orbit spacecrafts that are orbiting the planet?
Yep, exactly. So most of my work, or any person who's doing active studies on Mars, generally uses remote sensing datasets. I think the first time active surface processes were keenly seen was, I think, in 2006, when we had high-resolution datasets for the first time from the Mars Reconnaissance Orbiter. That was when features like gullies were first identified. People didn't know that like geologic features like gullies existed on Mars until then. It was only known to have existed on Earth. But then when they started getting repeat coverage over time, that is, say, they're trying to image the same region over and over again at different time periods in a Martian year, that is when they started to observe some changes between images. So they were quite reluctant to, say, attribute it towards a surface process in the initial phases. And they first predicted that probably there is flowing water on Mars that's actually causing these to happen. But then that interpretation has changed a whole lot since we repeatedly got higher resolution data sets from different spacecrafts, not just the Mars Reconnaissance Orbiter in the future. Now, currently, I think, the research which I'm currently focusing on tries to use these Mars Reconnaissance Orbiters as some sort of a background and focuses on active surface processes from much more recent data sets that we have, like from the ExoMars Trace Gas Orbiter that was just launched probably like 4 years ago. So that tends to provide us a hell of a lot more information as compared to what we knew about these active surface processes from these earlier data sets.
So I'm interested to know a little bit about, in terms of your own research, what tools do you use to sort of analyze these surface processes on Mars, and how does that look, given that obviously we're not, at least in the foreseeable future, going physically to Mars? Could you tell us a little bit about that?
So yeah, definitely. My research does not totally depend on a physical comparison approach, but I also use a technique called as remote sensing spectroscopy, wherein I'm trying to identify what agents are actually responsible for these processes to occur in the first place. Just simply comparing visual images might help us identify, okay, this is a region where change has actually occurred between two specific timelines. But then if we try to incorporate spectral information into this entire change detection scenario, it also helps us to identify what exactly has changed between these two images. Has the region become more mafic, or do we actually see some signs of water ice or frost, depending on the season in which that image was taken? So that somehow gives us some sort of an idea about what agent is responsible for the process itself. So yeah, that's.
And when you say agent, you are referring to like whether or not it could be like some sort of chemical, including water and whatever state it might be on Mars, and other types of substances.
Yeah, absolutely. Specifically, if I'm focusing on gullies, currently there are like two contested theories about what agents could be responsible for formation of gullies in the first place. It's a huge debate with respect to if all these gullies are actually formed by carbon dioxide frost or water ice frost, because most of these gully deposits are particularly seen in the higher latitudes, the mid to higher latitudes of Mars, which have at least recently been proven to have be host to potential subsurface ice deposits, at least for some distances below the surface right now. So this is a hugely contested theory. Initially, when they first detected gullies, they just assumed that it could be because of actual flowing water, and it became a huge discovery at that point of time when they first saw new deposits actually forming there. And especially because it's so very difficult to separate out between regions that are affected by water ice frost or water in the first place, because they both form hydrated minerals all along the deposit of the gully itself. So yeah, it has been a challenge till now, and still we don't have a clear-cut answer as to what agents are responsible for these gullies to form.
So you mentioned there's a couple of theories that have been posited that look at what types of agents form gullies. But what are your thoughts? What's your opinion?
So yeah, until now, even I had agreed on the carbon dioxide frost theory, but some of my research that I'm currently working on actually focuses on focuses on some gullies that aren't necessarily formed by frost at all. Because the main difference that we actually found here was for any gullies that are formed by frost, they usually exhibit an IR signature in remote sensing datasets, simply because of the 1,000 nanometer absorption that water and other hydrated minerals generally tend to have in their ferrous nature. But then we started seeing some gullies that were slightly yellowish in these remote sensing datasets, which we don't really have a clue as to what exactly is causing these gullies to form in the first place. Currently, we think they might just be because of sand just getting deposited and accumulated at the top of the slope. And that's basically just causing some sort of a slope failure and allowing all the huge amount of debris that is accumulated at the top of the slope to just fall down. So currently, I think, yes, most of the bluish sort of gully deposits might be due to carbon dioxide frost, but it might not be the only agent that's responsible for all formation of gullies on Mars.
And so what do you think is missing in the spacecrafts and missions that are currently around Mars that's needed to be able to confirm what agent could be responsible? Or I'm guessing it's going to be until we can actually get there on the ground, we're never really going to know what's causing the formation of these gullies.
Well, honestly, even if we get down to the ground, it's going to be difficult because these active processes, although they are active, they do have larger timelines of activity in a way. They're not instantaneous. So most gullies are generally active. I mean, their active period is somewhere around 4 months or 5 months or something. So unless we actually stay the entire duration of the gully formation, it's kind of difficult to ascertain what might be causing that. I think the basic limitation that we have right now is that in remote sensing datasets, I think it's always a trade-off between spatial and spectral resolution that you always have. The spectral resolution actually helps us determine what what minerals are actually responsible for an active process to occur. But if you actually want to look at the feature at a higher resolution, you would have to trade off the spectral resolution here. So ideally, I think in the near future, we should definitely have a higher resolution, a higher spatial and spectral resolution sensor if it's humanly possible, and that will be probably the best sensor that will help us detect these agents that are responsible for these active surface processes.
So what currently is the best spatial and spectral resolution? And if you don't mind, want to quickly explain for the audience, what do you mean by spatial resolution and spectral resolution?
Oh yeah, definitely. So spatial resolution, as such, is the smallest size, the smallest area on the planet that is visible by a spacecraft or by a specific sensor, for that matter. And spectral resolution is basically the is an equivalent of the number of bands that a sensor has that it can see the surface in. Currently, the best spatial resolution dataset is the HiRISE on the Mars Reconnaissance Orbiter. That that provides us images almost up to around 25 to 50 centimeters per pixel. But there's a caveat to this, though, especially when you're dealing with active surface processes, because these are not localized to smaller points or smaller regions on the surface. So because HiRISE has such a large spatial resolution, it has a much smaller footprint or a much smaller swath as compared to most other sensors that are available on Mars. So it's not always possible to cover the entire region where change has occurred with HiRISE. So to complement that, on the Mars Reconnaissance Orbiter itself, we have the CTX, or the context imager, that provides us a panchromatic information at around 6 meters per pixel. Now, more recently, from the ExoMars Trace Gas Orbiter, this is probably the best sensor that is available right now for seasonal and change detection studies, because it provides us both color and panchromatic datasets at roughly around 4 meters per pixel. That is not really bad, at least when you're trying to identify large-scale change detection features here. So this has actually given it a huge edge over high-rise in the recent past. And to be honest, high-rise has been operating almost for 14 years now. So it is an aging sensor, and there is a definite need to move towards a much newer sensor if you need to continue change monitoring processes, because this is not time bound, because there is change occurring on Mars almost every single day. So you do require regular time series observations from a particular sensor, at least in the near distant future.
And what do you think is sort of holding us back from moving to a new and more sophisticated sensor?
Actually, it is not actually holding us back. My research at Western here is actually trying to bridge the gap between HiRISE and CASIS on the ExoMars Trace Gas Orbiter to sort of give a new method that blends into both, to using both datasets for such change detection processes in the future. Now, since the Trace Gas Orbiter has just been giving us data from the past 2 years, it is really difficult to have that sort of a regular background datasets to actually have to start tracking from, right? You need some sort of background from which you can compare images and then see, okay, this is where a change has occurred, and have a regular monitoring sequence starting forward. So I think nothing is holding us back right now. I think it's just people are just beginning to appreciate the importance of color or the importance of spectral information in such change detection campaigns.
Mm-hmm.
And speaking, I think since you mentioned CASIS, from the bio that you sent us, it said that you've actually gotten some hands-on experience working with the mission, which is currently ongoing, and getting to learn more about how images will be acquired on the surface of Mars. So do you maybe want to quickly tell the audience a little bit about that experience?
Oh yeah, definitely. I recently actually got a chance to plan images for the CASIS orbiter just early in December. So it gives us a huge opportunity for us to exactly target where you want an image and what are the image parameters that you necessarily want. Now, CASIS is basically a 4-band imaging sensor as compared to HiRISE. The huge advantage that CASIS provides over HiRISE is that it has a much larger color swath as compared to HiRISE. The narrow HiRISE color strip just covers about 1.2 kilometers surface, as compared to HiRISE that covers roughly about 6 to 8 kilometers on the surface. So it allows us to view a larger surface area in color. Now, this allows us huge flexibility as well during planning too, because it allows us to define which filters are required for a specific image. For example, if you have like a cool outcrop in a central uplift or something, wherein compositional information is really critical for us to understand how that feature is evolved, it allows us to capture that image in 4 colors, while morphologic targets, like if you're just trying to understand flow features or how impact melt has sort of like moved across the surface, you're trying to estimate the boundaries of different surface units. It allows us to cut back on the number of bands that are required. You can choose a 3-band combination or a 2-band combination in the sensor itself, and provide a much wider color coverage as compared to the narrow 4-color coverage that you generally have for uplifts.
And for the audience, can you just explain a little bit about what bands are?
Oh yeah, definitely. So bands are essentially different spectral channels that are available on a particular sensor. That is, like CASIS has 4 bands: the blue channel, the pan channel, the red, and the NIR channel. So what this means is it's something similar to a microscope that you have on the lab. It's just a mini version of the microscope that you have on the satellite. So these are the 4 wavelengths in which it can detect spectral reflectances or responses from the surface. and it can characterize and quantify them into some sort of a digital number that is basically an estimate of what is the brightness of the surface in each specific wavelength in that electromagnetic spectrum.
And when you mentioned when you're looking at planning all these images, you mentioned changing it from narrow swaths, which I guess is the area that the camera can cover every time it's activated, into a wider swath. So so how narrow are we talking here?
Okay, so yeah, talking about pixels, say if you do really want all the 4 filters on a specific Cassis image, you really can't go above a filter width of somewhere around 1400 pixels per channel, the filter width. But then if you only require 2 colors or 3 colors in an image, you can extend that filter width to almost up to around 2048 pixels for each filter. So that gives us a huge, a distinctly wide color image as compared to a very, very narrow 4-color image that you have for other regions.
Okay. And it's really cool that we get to hear that students are actually able to get hands-on experience in these like real planetary missions, because a lot of the time it's usually just a dream people think of. It's like, oh, I don't know if I ever be able to get to work on a mission that's actively going. And since it sounds like a lot of your work involves just looking at images, processing them, and trying to understand what it's showing. So I'm guessing when we've been asking this a lot recently with COVID-19 keeping everyone at home and majority of the time off campus. So I'm guessing for you, it's not had as much as an impact, since you just have to look at images and doesn't require any lab work.
Yep, actually that's true. I have not been hugely impacted by COVID, except the mental sort of impact that COVID has brought about. It has not hugely impacted physically my research as such, because most of my work is dealing with remote sensing datasets. So I still have access to all these datasets right from my laptop. So yes, it has not hugely impacted my research as such. Yeah.
And do you need a special software to access this kind of data? It sounds like it would have to be quite sophisticated, I would imagine.
So yeah, there are certain encrypted software that are generally used for planning and for downloading these datasets, which are proprietary of the mission specialists themselves. This is simply because Cassis datasets are not are not available to the public just as yet. So you don't really require a software to access and use them. You can still use them in general image processing softwares like ArcGIS or Envy for that matter. But to acquire and to get the datasets and to download the datasets itself, you do require some special permissions. That are usually the people there at Bern who actually develop the sensor they provide us.
Okay, that's really cool, and I think everyone here wishes the best of luck for your research. And unfortunately, we are just about to run out of time. So before we go, do you have any social media or websites you'd like to shout out for the show?
Oh yeah, definitely. I constantly keep posting on Twitter about various research advances that I've been having, and even the planning missions that I've been a part of. So you can actually follow me on Twitter on Vidhya @Vidhya Ganesh R93. Let me just spell it for you: VIDHYAGANESHR93.
Okay, we'll make sure to add that to the show notes for everyone, and make sure everyone follows Vidya to learn more about Cassis and surface processes on Mars. This has been Gradcast, the official radio show and podcast of the Society of Graduate Students here at Western University. I've been your host, Gavin Tolometti, joined with Elizabeth Mohler as my co-host. We have been speaking with Vidhya Ganesh Rangarajan, who studies Earth and planetary science at Western University, and this episode was produced by Ariel Frame. If you'd like to learn more about the show or maybe come on as a guest, you can email us at gradcastradio@gmail.com. You can go on our website to find all of our episodes at gradcast.ca, or you can follow us on Twitter, Instagram, Facebook at Gradcast Radio. Thank you for listening and have a great night.